right, let's talk some more about a simple harmonic oscillation. So this is, again, just a generic plots of our functions of x of t. So again, this was xm cosine, right? Xm cosine of all of our stuff. Here we have a negative omega xm sine of that same, and then here's a negative omega squared xm, again, cosine of all that. And you can see the function. So our position, we start with our positive position. At that location, we have zero velocity. So when the thing is at this position, it has zero velocity, but it has maximum negative acceleration at that point. And so we have a non-zero position and acceleration, but we have zero velocity. Whereas when we get to the zero of our position, we actually have maximum magnitude of our velocity. It's actually negative, but we also have negative acceleration. This is the equilibrium position. And then we can go through and do that. So if you think about it, at time equals 0, we have a maximum amount of spring potential energy. Our x naught is equal to xm. We have spring potential energy, which is 1/2 k xm squared. We have no velocity, no speed, and so no kinetic energy. So the total mechanical energy at time equals 0. Let's see if we can set this. So here we have maximum potential energy there. All of our energy here is this, but then when we let this go, what we see is that we actually are switching off kinetic and potential energy all over the place. I love this diagram. There's so much going on here. Right? As we look at our kinetic energy and potential energies, they are also sinusoidal, and we just have energy going back and forth between kinetic and potential and kinetic and potential over and over and over again. When we get to time equals to the period 1/4 the period, now we're at 0 displacement, right? And that's here. Our speed, and so we have 0 potential energy, but we have a speed at that place of negative omega xm. So our kinetic energy is 1/2 the mass times this thing squared. Well, that thing squared is omega squared xm squared, but if we remember that omega squared itself is k over m, this is again just 1/2 k xm squared. The kinetic energy is equal to this again. And so we see that this is the total amount of energy that our mass on a spring has. It's the total amount of mechanical energy that the mass on the spring has. At any x, the total amount of energy, mechanical energy, is this. And so we can say that at any x, the energy would be the kinetic at that location plus the potential at that location, but the total has to add up to this. So the difference between this xm and this x, this could be any x, this is the maximum x that you could have. So we can solve this. Let me rewrite that. Looks like a big V. We can actually rewrite this and get an equation for what the speed is if we happen to know the displacement instead of the time. Say I wanted to know how fast something it was moving when it was at its position, rather than saying how fast it's moving at a certain time. The other equation I have for V is V as a function of t. Now I have V as a function of x. It's not really what this question is asking, but let's go ahead and look at it. So here, this is kind of distracting. Let's look at number 31. It says a mass equal to 5 kilogram object on a frictionless horizontal surface is attached to a spring with a spring constant of 1,000 newtons per meter. The object is displaced from equilibrium by 50 centimeters, but it's also given an initial velocity of 10 meters per second back towards the equilibrium position. So this is not XM. This is not the maximum thing it's going to have. In fact, maybe this isn't a terrible thing to get rid of. Let's reset this. I don't know. I can't change the K here, but I can say, well, if I move this to, say, 50 centimeters, and then I say, okay, I'm going to make it go backwards with, I don't think I can make it go all the way up, but let's just say I make it go backwards with velocity. I want my velocity to go this way. Is this going to let me? I think so. Say I wanted to go this fast, 5 meters per second back this direction. Let's see if this does this. It's going to go further than my original displacement. It's hard to see that on this simulation. So, but if I give it more speed, it's actually going to be able to go further than 50 centimeters when it gets back to this position. And so what I really want to do is say, what is my initial energy? So my initial energy is my initial kinetic energy and my initial spring potential energy. So I have 1/2 5 kilograms. The initial speed is 10 meters per second squared. And so I end up with 0.5 times 100 times 5, which is 250 joules. And then here I have 1/2, the K is 1,000. And then the initial displacement is 50 centimeters. So 0.5 times 1,000 times 0.5 squared is 125 joules. And so my total initial mechanical energy is the combination of these, which is 375 joules. That's the maximum amount of energy that I have. Now, the total amount of energy has to equal 1/2 K XM squared, but I don't actually know what XM squared is. I also can find, just a second, somebody's calling. Sorry, I'm back. So this is actually the answer to the initial potential energy of the block. This is part B. The initial kinetic energy of the block. This is part C. The motion's frequency, that's F. Well, if I know K and M, which I do, then omega is the square root of K over M. Right, if we go all the way back over here somewhere, yes, square root of that. And we could even do frequency from this. We could say frequency is 1 over 2 pi. That make things happier. So I can just say frequency is 1 over 2 pi K over M. I'm plugging in my numbers I get. So doing that, I get 2.25 hertz for the frequency. So that's part A. Yeah, so part A is the frequency, B with the potential energy, C is the kinetic energy, and so the motion's amplitude, that's XM. So if we know, and again, that's where we can use this equation. So the total amount of mechanical energy is 375. We can get that xm is the square root of 2 times the total mechanical energy divided by k, which comes out to be 0.866 meters. So this one was a little different than our example above. So if you pull the spring out and then you give it some initial velocity, then it has more mechanical energy than just spring potential energy initially, right? If it only had, if you pulled it out to 50 centimeters and that was all the energy it had was the spring potential energy, that's one thing. But if you pull it out and you give it some initial velocity, then it has kinetic energy and that potential energy. This is the difference between taking a ball at the top of something and dropping it. If you drop it, then the only energy it has is gravitational potential energy. But if you throw it at the same time, then it has kinetic energy and potential energy. And that's what we've got going on here. All right. Another example of simple harmonic motion, another traditional example, is a simple pendulum. There's technically a difference between different types of pendulum. A simple pendulum is essentially just a string with some sort of mass at the end, which is often called a bob. There's also physical pendulums and conical pendulums and things like that as well, but this is a simple pendulum. And yeah, we can look at a simulation for this as well. So there's really a lot of comparison between, say, a simple mass on a block connected to a spring and a pendulum. Again, you have, for a spring, you have the spring is our restoring force, which is trying to pull it back towards the middle. With a pendulum, it's gravity. Gravity is trying to pull it back. There's always some component of gravity that's trying to pull it back towards the center, except when it's actually at that center location. Then gravity is just pulling straight down. But along the way, there's a component trying to pull it towards that center location. Again, we have kinetic and potential energy switching back and forth between the two, but our total amount of energy stays the same. I'm not going to do the derivation for the simple harmonic motion period in omega for a simple pendulum. It's a little more complicated and it's a little uglier and it has a couple of more caveats to it, but what you kind of end up with as the takeaway is that the period of a pendulum is dependent upon the length of the pendulum, capital L, the length of the string, divided by G, the square root of that. So it's not the length, it's the square root of the length. And that really, it pretty much only depends upon that. It doesn't really depend upon the amplitude as long as your amplitudes here are fairly small. Small angle approximation is a term we would have to use in the derivation, which I don't think you guys want to hear. So I always say that those words will empty a room. So the period really, in here, this case, really pretty much depends on the length and then the gravitational force, how much gravity is pulling down. So in other words, this would be different if you took this to, say, the moon or something like that. The actual equation of motion isn't x of t. It's going to be theta of t. How is this angle changing with time? Or there's some maximum amount that it's displaced. Again, times the cosine. And this part is pretty much the same. It's just what we have out here. There is some energy that it has, some y sub m, which is the maximum height that it rises above. Y sub m is going to be L times this function here, 1 minus the cosine of theta m. I think I proved that about a pendulum several weeks ago or months ago when we were doing energy. We talked about that. So the maximum height is L times 1 minus the cosine of the maximum theta. And so our total mechanical energy is mgl 1 minus the cosine. This is the amount of energy that the highest point. This is the energy at any other theta. So again, this is very similar to me talking about, the energy for our mass on a spring, and then this is the mass at any other point besides the maximum displacement. And so once more, we can find an equation for V as a function of position, theta position, based upon energy. And number 42, let me do that one real quick. It says a simple pendulum consists of a small 60-gram bob at the end of a cord of negligible mass if the angle between the cord and the vertical is given by this. So this is that equation. So my theta as a function of time can be written as 0.0800 radians times the cosine of 4.43 radians per second times time plus some phase constant that we could add onto there. So this is my theta m, 0.080 radians. And then omega is 4.43 radians per second. Well, omega, so 2 pi f is omega, and 2 pi f is another way of writing 2 pi over t. And omega, actually, we read it, so writing this back again, the period then is going to be 4.43 radians per second divided by 2 pi. Actually, it's the way around. If I move this around, if I write that over there, it's 2 pi divided by 4.43 radians per second. So let's get that math. Okay, that's 1.418 seconds. And then, this is really doing it the long way, but t is equal to 2 pi over lg, 2 pi the square root of L divided by G. So then the square root of L divided by G is 1.418 seconds divided by 2 pi, which is why I should have done this in a shorter way, because I just multiplied by 2 pi, divided by 2, divided by pi is 0.2257 seconds. And then if I square everything and multiply by 9.8, I end up with 0.499 meters. So this could have been done shorter. I could have just said that basically that T is equal to 2 pi over omega, and that T also has to equal 2 pi the square root of L over G. And so I could have canceled these 2 pi's and solve for L that way, which is essentially what I did with just a longer way. What else does it want to know? So the pendulum's length, we just got that. And the maximum kinetic energy, well, the maximum kinetic energy is going to be the same as the U maximum, or the total mechanical energy. And the total mechanical energy for this is mgl 1 minus the cosine of theta m, right? So this should be mgl 1 minus the cosine of theta m. So putting this all in here, my mass is 60 grams, which is 0.06 kilograms, times g, times the length, 0.499 meters, 1 minus the cosine, and my theta m is 0.08 radians. Now, this is actually one situation where I'm going to try to take the cosine of something in radians. So I do need to have my calculator in radians to do this. So I'm going to go down to my calculator and punch in that I want radians. I'm going to say 1 minus the cosine of 0.08. That term is pretty small. Times 0.499 times 9.8 times 0.06. And I'm getting a really small kinetic energy here of 9.38 times 10 to the negative 4 joules. Just a second. Yep, that's our answer. This is a really tiny amount of maximum kinetic energy. All right, that's all I'm going to do in chapter 15. It's essentially, just some, I think the sample problems I just did are pretty typical of the ones I assigned. Some of them are the ones I assigned. We can try to go over some of this in class on the first Tuesday as well. All right, I'll move into chapter 16 and 17 next.